Good morning, everyone. This is Jim Chastain with EasyPower. Welcome to the Tuesday refresher. As I indicated, this is the first post-eclipse refresher session, so we may be a little rusty. Today we're going to talk about modeling DC hybrid systems in EasyPower, and the subject is significant in several ways. First of all, EasyPower models AC and DC in the same module, whether you're working on short circuit, arc flash, coordination, or power flow. But there's some elements that make the chore different than what it is in a standard DC circuit. So as we jump into this, I'd like to start with a couple poll questions. First of all, how often do your projects include DC elements? And then which components do you use the most? So appreciate your feedback. Let's go ahead and launch the poll. Take about 15-20 seconds to collect some responses, if you would please. We do appreciate your participation. It helps direct both our conversation and, in some regards, some of the effort behind the scenes in amplifying the tools themselves. I appreciate everybody participating. So here's what it looked like as far as the responses. Glad to see that. And then secondly, what elements are usually included. And we see more and more people are seeing hybrid circuits for analysis and design, and they're growing in capacity virtually with every project. A lot of systems now are going into commercial establishments that may or may not have been that involved with arc flash before. And so we're seeing a lot of people having to deal with systems that necessarily or didn't have to label their arc flash previously. Here's what the responses were here. So let's kind of get into our discussion and see what happens. Now, as I kind of mentioned, the topic is tricky because what we're going to find is there's bidirectional current flow when it comes down to analyzing a fault compared to the normal current flow for typical operations. And this requires bidirectional protective devices, which is not so much a problem with fuses, but it can be a significant issue when it comes to low voltage power circuit breakers or even multi-case circuit breakers. The fault currents also in the DC side of things will often be on the same order of magnitude as load currents. So that means we're talking about some protective devices that will take a long time to trip because there's not this large difference in fault current versus regular normal current, which means some protective devices actually may not clear the fault at all, and it complicates both the modeling and the analysis. So what I'm going to do, rather than talk about rules of design, in fact, we're really not talking about design at all. It's strictly how to utilize EasyPower tools to both analyze, correctly model what you have, and then analyze it in terms of protective devices. Frequently, this involves a unique feature in EasyPower, which we refer to as integrated method, and I'll spend a little bit of time describing that. Also, there's a feature that's been recently added in EasyPower 9.8 where you can designate specific upstream devices that the bus is responding to rather than the normal top-down current flow. And again, these are not rules, but it's more a focus on process and a way to kind of use the tools to find the clues to what may be interfering with your ability to complete the analysis. So the mystery or the story all began with a customer that was wanting some assistance, and his particular design had a bank of batteries and a bank of PV arrays in conjunction or were tied into the utility supply. So it was a mini microgrid situation, and that's where we're going to start the discussion. So right, this is what the one line looked in EasyPower. And the point of concern, or the main point of focus, at least on the initial question, was how do you calculate or what's wrong with the calculations in arc flash on the main switchboard? So if we go to short circuit focus, fault the buses, and we look at the incident energy, we can see it's huge. And for a 600 volt system with maximum of 400 amps in each leg, it doesn't make a whole lot of sense. If we look at the currents involved and we fault this bus, we see we have 49,000 some odd amps coming from the utility, and then 460, 470 come from the downstream loads. So right away you can see that something's not quite making sense. And so for starters, we're going to open these breakers and try this all again and look at the incident energy. And at that point, we show that we're getting at least civil levels, less than 4 calories on the main switchboard. So that brings up a problem. How do we resolve what's going on? Clearly there's something amiss downstream from either one of these legs. And so in the process of collecting clues, the first place I like to start is with the arc flash hazard spreadsheet, which is displayed on the one line if we use the arrange for arc flash icon at the top. I'm going to double click on this one bus so that we're isolating what we're looking at there, and we can see with both of the loads or the downstream breakers open that BL13 is our tripping device, is our device that's limiting the arc current, and that it leads me to look at the way that the arc flash hazard tab in short circuit options is set up. Well, for starters, we've got this set up as detailed, so I'm a little suspicious of that. So I'm going to set excluding main, because at this point we don't know for sure that this breaker, the main breaker, has an arcing barrier between the main bus and its incoming terminals. So if we apply that, that means as we fault this bus, we still see BL13 as our limiting device. So that causes some concern. So let's go back to our database edit, look at the main switchboard and the arc flash, which is set up to calculate normally, and we still have our arc flash output set to detailed. So I'd rather take this back to use global options, at which point we're ready to go to short circuit focus, fault this bus, look at our arrange for arc flash, and now we see what we expect to see, and that is we're excluding the main breaker. It's relying on, well, we're not excluding the main breaker. And so why is that? Let's go back and look at a database edit. All right, this is an insulated case circuit breaker. It's got trip settings, and at that point, I would go back and double check my figures on what the type of breaker this really is, because we're really not, I don't think we're in the realm of justifying what the insulated case circuit breaker is really meant to do. We go back to our upstream breaker. Again, we have the same issue here, and I would seriously reconsider what my data collection team is telling me about these two breakers being 2,000 amps. But with that said, the question still arises: why is that main breaker not being excluded? Go back to short circuit, double click the bus, look at incident energy, and then our short circuit options. So at this point, I start to suspect I have some problems as far as the construction of the one line. As I kind of clear this particular problem, we'll come back to it in a second. Let's go ahead and connect the downstream buses. You can see my energy jumps up quite a bit. What happens if I disconnect the main breaker, I can see now my calories falls down, and now I'm being protected by BL10. It's like, where the heck is BL10? So if we go into our low voltage power circuit breakers and look for BL10A, we can see that it's over here in our battery bank. And so that doesn't make a lot of sense if we look at the current involved in, we only have 700 amps and it's taking over 1,000 seconds to clear. All right, so clearly we've got some issues as far as how we're designating the timing and the way the direction of the current's going to flow. If I fault this bus, this is interesting. All right, I'm faulting the bus, the main bus on the DC battery bank where all the batteries are collected, and there's 82,000 amps DC current. How can that be? Well, I've got 6,000 per, and it looks like I've probably got 12 different batteries. So yeah, that number does make sense. If I go a little further into the mix and we'll look at incident energy, I'm not getting anything calculated here on my individual battery. If I go look at the database setup, it's set up to calculate normally. This particular fuse I moved so that I could verify what the difference would be if I put my fuse there. The point being, this fuse is not going to indicate at all because there's no downstream bus to fault. Whereas if we fault if we move the bus protection or the battery fuse upstream of the designated bus, we should be able to get an indication there of what's faulting. Okay, so at this point I decided I needed to redraw the whole one line. So and at the very least move the fuses to the other side of that bus. And so that brought me to a drawing that looks something like this. Pretty much the same element. The difference being, when I go into short circuit focus, I mentioned earlier that normally we use momentary current for doing arc flash. What that tells us, and what we can see by the way the calculations are being made, when I fault this bus, what we're seeing is the indication of the protective breaker in play, but it's also timing out the last device to clear current. So even though most of our current's coming through this main breaker and it's tripping relatively fast, the calculations in with the momentary current include the contributions that are coming from these downstream legs, and they may not clear at all. In fact, we're showing a trip time of 5 seconds on the inverter, which is on the battery bank. The solution to that problem lies in the setup, rather than momentary, to use integrated. And in this mode, for the arc flash, let's come back and do this. I'm going to go ahead and look at instant energy on this bus and then change that particular setting. All right, so we're using the momentary current, which is the highest current for the fault, and it'll be somewhere near 50,000 amps, and it's going to be calculated until the last protective device clears, in this case 5 seconds. And that's what's giving us a problem. So if we select integrated, we use half cycle current for the first half cycle of the fault, 5 cycle current for the next 5 cycles if we have a long extinguishing period, and then long-term current for the balance of the fault. So as we apply this, we see our incident energy drop down dramatically. Nothing's changed as far as the fault clearing time here, but the incident energy changed because we're not using the full magnitude for the entire length of the fault. If I isolate each side again, I can see now if a fault occurs on this bus, and again, I'm going to see the 49,000 amps, 48,000 amps, and it will clear my protective device, which is BL13, in 35 milliseconds. All right, so that's giving me better than 4-calorie protection. As soon as I add the battery bank, that's bumping my calorie count up, and so that leads me to believe we need to look at what's going on the battery side of things. So I'm going to fault all the buses, and let's look to see if we have any other issues bus-wise. So there's exactly bus 11 looks like it's kind of having a weird calculation. So let's go look at bus 11. And sure enough, it's over here on our battery. Now, so the difference between what we started off with and what this version shows is now I have my fuses upstream of the fault or the bus connection to the battery, where I really need my protection. And in fact, the battery's only supplying 7,000 amps, but if there is a fault at this location, potentially it could be pulling in the entire 65,000 amps from that battery bus. And consequently, the fuse that we have upstream of that bus will protect the battery and or people in the area, because now it's going to trip in 15 milliseconds, which gives us something better than 6 calories per square centimeter. All right, takes us to the main bus, the main battery bus. And if we fault that, we see that it's 7-calorie exposure. If we fault the next bus up, 6 calories. So for the most part, and it's here again is where I have a little bit of a concern. We're showing that the fuse is going to be the device, or one of the fuses is going to be the element that clears this fault, and clearly that's not the case. We should be, I don't know if there's a protective device built into the inverter or not on the DC side. And so my suspicion is I need to go back and look at the data sheet for the inverter, because if it doesn't have protection, then I may need to include a fuse for the total collection, and or look at whatever mistake I may have made in my data collection, because clearly the 80,000 or 60,000 amps that we're seeing on this collector bus during a fault probably will not be cleared by an individual fuse. Just one concern there. We come back to the other side of the inverter, and let's kind of go upstream here. If we have a fault on this bus, we see that it's being protected by the inverter itself, which has a time limit of 5 seconds, according to the data that was entered. Let me kind of go to that point. So on the AC side, the faulting current will be 2x the full load current, and according to the IGBT specs, it'll clear in 5 seconds. So that's what we're seeing protecting this bus. The next point of concern is what's happening upstream of that. Oh, one more thing before I leave the batteries. When I come back and look at the way this bus is set up, and I'm looking at one of the upstream buses between the battery and the fuse, normally it would be looking downstream for the arcing protection, but downstream from the AC side means that there's the battery is the next element up there. So the EasyPower tools allow us to define on the one line what the protective device is that we are relying on. And so we select user-defined one-line device, and we pick out the specific, in this case it looks like FS1B as the element for that particular bus. And in this case we're using the global options for the rest of the settings. So each of these buses now is going to have designated arc flash protection by that next upstream fuse. So that's unique and hasn't been a feature in EasyPower prior to the last update in 9.8. If we come back to this bus, which will be again upstream, we're saying we're going to auto-calculate here. We have a problem in that it will be susceptible to fault current from the main switchboard and also fault current from the battery side of things. If we go into short circuit focus, let's go ahead and look at current. We fault this bus. Again, it'll see 45,000 amps coming from the utility, 470 amps if the battery contribution, and so the incident energy will be effectively, because we're using the integrated method, it will use the short circuit current from the utility for the first half cycle, and then the balance will be protected by the short circuit that the inverter is supplying, the protection of the server. So the fact is that we have a 7.9 calorie protection is probably not just valid, it's probably a good idea. Now, the other, and I have this, you can see there's about 1/10 of a calorie difference if I include the PV side when I'm doing each leg incident energy calculation. The point I wanted to make is that there also is a potential for evaluating scenarios that include one or both of the other two power sources. So does the situation change if I take off my utility and my PV bank? Do we ever operate in this mode? Well, as I understand it, the answer is no. It's always a combination of the utility plus one or the other or both. So at this point, I'd want to create a scenario that allows me to open one breaker, evaluate arc flash and equipment duty, and open the other breaker and close the first one, and consider those three different combinations of breaker styles. Okay, so where does this leave us? First of all, we're utilizing integrated method because it's going to be more accurate in terms of these long fault clearing times. We've specifically designated which tripping device will protect, in this case, the batteries from a fault upstream from a total collector. We've also identified a potential that either we need another inline fuse for the total current, or we need to understand what the inverter can protect us for from that group contribution. On the PV side, a similar but different set of conditions exist, and if we take this offline and fault this particular bus, we can see it's being protected by the inverter on the inverter 1, which is down here on our collector. Same kind of concern, at least on my part. If we looked at the current involved for a fault here, we see 3,000 amps from the utility, but 115 amps from the array, and this ends up being somewhat artificial, and it will vary, depends upon what the manufacturer's data sheet says. But the question is, do we have adequate protection when it comes to this collector bus or this totalizer bus being summed up? It's going to see a total of 6,000 amps, most of which is coming from the utility. So if we open that and look at incident energy on this panel board, we see it's less than 0.3 of a calorie. So the actual contribution and the danger from just the PV array itself is relatively small, as long as we've got the inverters in the circuit. If we go back to the utility side of things, because we're excluding the main BL3, we're counting on BL1 as our trip device, and so it's doing its job. The question is, based upon how this is set up, can we include or can we exclude? Which should we do on this particular panel? If we know that, in fact, we can include it, we would go to this local bus in the database editor, change its arc flash to including main for just this local bus, go back to short circuit, and when we fault it, we should end up with hopefully a little better situation. So yeah, we have BL3, and it looks like it has an arc time of a couple seconds, which makes me wonder if it's set up right. The last clue in kind of ferreting out the mystery of the protection system is sequence of events in coordination. If we go into coordination and we look at a current in a single bus fault, let's fault this particular bus, it tells us what the current is, and the sequence of events report, which we can show here, will show us what the tripping time is for all chronological order, everything upstream. If we close and include the other leg, I want to see how it complicates my situation. So we close it. Let's go back to coordination. Fault this bus and this one bus. Look at our sequence of events, and it's easier to see this on a report. This is just an example of how convoluted the issue becomes, and most of these DC protection or the remote protective devices really won't clear at all because they don't have enough current going through them. So that gives us some guidance in terms of how to set up the scenarios. All right, so I got a couple, and then finally I want to use my coordination to pick out these breakers and this downstream breaker here, and my breaker here and this bus. And let's plot this, see if I got it all. The little graphic that I put over the cell is getting in the way. So let me take this out. It becomes opaque when I go into a plot. All right, I want to pick up this bus, this breaker, this transformer, and let's go ahead and pick up the guys up here. I can't tell if I got them all or not. Yeah, let's plot them. Okay, so the point I'm making is if this panel board faults, are we really getting coordination for the upstream devices? And what we're saying is that BL3 is the protective device on a fault at that point. I missed my main breaker. Let's kind of come back and do this. I'll include this guy here. One more time. There we go. Now, when we fault the bus, which again is behind my graphic right there, and insert the arcing current, you can see I got more than I wanted. I would expect the downstream device to be the protective device in play. So obviously I could do a better job of coordination because here I have my current being protected by BL1 when apparently if BL13 were in the circuit or BL3 were in the circuit, both could do a better job of protecting the downstream circuit. So I may have some coordination issues that I need to deal with. And again, they're not going to show up if I'm looking at the whole system. Okay, so we've run long. I've kind of circled around and I think been a little bit less than clear, but let me kind of reiterate the point. Evaluate the benefits of using integrated method versus just the momentary current, primarily because it does a better job of explaining or utilizing the actual current during an extended fault. Utilize designating upstream devices when the tool can't necessarily understand which direction the fault is coming from in terms of arcing faults. And I encourage you to use this as a method to kind of anticipate what your results could be rather than just look at the first result coming out of the tools. So the things to use are the Arc Flash Hazard Report. We didn't talk about the database browser. There's a lot of information. Let me jump back real quick. There's a lot of information available if we kind of go back to our database edit. In the database browser, there's a lot of information specifically on buses, and I don't want to go into configuration, I want to go into buses. I can see that we failed to include a lot of the bus rating when we set up the one line. We're having specific rules for a series, and this will be where I'm talking about where I've directed the protection to be in one direction or a specific device. And it's also giving us the elements that are using the TCC curves versus some specific time limit, for instance. So a lot of results can be derived from just looking at the database browser, including the symmetrical current on that bus. And again, this will give you the ability to verify that you have the system modeled correctly and your protective devices, at least in the model, more represent what the fault current flow would be during a worst case event. All right, so I meant to include that before. We talked about short circuit options in the Arc Flash tab of the choices you have there. That's where you select the integrated method. Sequence of events gives you an idea of how convoluted and the multiple sources of fault current that the tool is looking at. And Scenario Manager may be utilizing Scenario Manager to configure different operation modes of the system will give you the ability to limit some of that variation. So hopefully you got something out of this. I apologize for not being more specific, but it really is, it really does boil down to, in many cases, the data collection may not be adequate to understand all of these variables that are included in hybrid systems, and you may need to have more specific information from the different components, specifically protective devices and inverters and rectifiers. Appreciate all for attending, and I encourage you to visit the website if you have questions on modeling or analysis in both hybrid or typical arc flash situations. By all means, contact tech support at easypower.com, and then keep up with the website in terms of other announcements for regional training, other webinars, and then look for updates and links to recorded webinars. Thank you for attending.